Hi guys, Justin here from chemistrynotes.com, and this is video number 3 from section 17, Electrochemistry. Now, I always like videos like this because today there's nothing really new. There's no new concepts, no new terms. We're not learning anything new in this video, but we're just kind of rehashing and practicing stuff from videos 1 and videos 2. So I always like these. They kind of hammer home the concepts. So without further ado, I'm going to do 3 galvanic cell practice problems. The first one is kind of its own standalone problem, and then examples 2 and 3 use the phrase completely describe. Completely describe the galvanic cell. And when we're told to do that, there's a certain number of things we have to report, or a few things that we're required to answer. So I'll talk about that when we get to it. Right now, let's just talk about example 1. All right, example 1. A galvanic cell is based on the following unbalanced equation. MnO4 minus plus 8H plus ClO3 minus yields ClO4 minus plus Mn2 plus H2O liquid. It has that redox reaction look to it. It is, of course, a redox reaction. And we are told, we are asked to do the following. We want to produce or give the balanced half reactions, the balanced overall cell reaction. We're asked to calculate E cell, standard E cell, and give the cell's line notation. Now remember table 17.1 from the last video? We always have that handy. We're always able to look up the reduction potential or flip the equation and get the oxidation half reaction potential. So under that little squiggly line there, it says half reactions use table 17.1, and that was from our last video, S17E2. And if I look at this, okay, I see my I see my manganese and my manganese 2 plus. I see my Cl on the left, my Cl on the right. These are the guys I need to focus on. When I do that, my anode half reaction, which is where oxidation occurs, I find it on the table. It's ClO3 minus plus H2O yields ClO4 minus plus 2H plus 2 electrons. Where did all that come from? I found it in table 17.1. And the oxidation potential is negative 1.19 volts. If I find the reduction, it's MnO4 minus plus 5 electrons plus 8H plus yields Mn2 plus 4H2O. That has a standard reduction of plus 1.51. All right, so what to do with these? Well, at the top of the page here, you can see I'm writing down the MnO4 minus equation again, but I'm doubling everything. Why am I doubling everything? Well, I want 10 electrons on both sides. So 2MnO4 minus plus 10 electrons plus 16H plus yields 2Mn2 plus 8H2O. You notice that my reduction still says 1.51 volts. I didn't multiply that through by 2. We don't do that like we do with delta H or delta G. Next equation, I have 5 ClO3 minus plus 5H2O yields 5 ClO4 minus plus 10H plus 10 electrons. Oxidation, negative 1.19 volts. Also, nothing gets multiplied through for my potential on that. Now, I have 10 electrons on both sides. They go away. Very important that electrons don't show up in the end. I cancel like terms just like we would in the math class. My balanced cell reaction, 2MnO4 minus plus 5 ClO3 minus plus 6H plus yields 2Mn2 plus 3H2O plus 5 ClO4 minus. Now, let's sum up the reduction and oxidation half reaction potentials. Thank goodness it's a positive voltage, right? 0.32 volts. All right, so now the line notation. Line notation. So we're going to use this in lieu of sketching of galvanic cell. So I have platinum solid as my inert electrode. More on that in a second. And then I have ClO3 minus, ClO4 minus, and H plus in that anode compartment. That's where oxidation is occurring. Double lines, which means a compartment divider. So in the cathode, I have H plus, MnO4 minus, and Mn2 plus in solution. my electrode is also an inert electrode, platinum solid. I didn't have manganese solid. I didn't have some sort of solid. I didn't have like a copper solid or a zinc solid that was a participant in the oxidation or reduction, did I? I got to have an electrode of some sort. So what's PT solid? Well, that's platinum, of course. PT's symbol is platinum, and it's an inert metal that must be used as the conducting electrode when there's no metal such as zinc solid or copper solid or Fe solid. Okay, so when there's no metal involved in the anode or cathode half reaction, well, then we have to use something. We use an inert electrode that won't interfere with our redox reaction, so we use platinum, PT. There are others. All right, example 2. This is example 2 of 3 in today's video. Here's that term or that phrase, completely describe. So I'm going to tell you what it means to completely describe a galvanic cell. First, let me write out the equation. It says, completely describe the following galvanic cell, given just its half reactions. So here are the two half reactions. Fe2 plus 2 electrons yields Fe solid. It has a reduction potential of negative 0.44 volts. And the next one, MnO4 minus plus 5 electrons plus 8H plus yields Mn2 plus 4H2O. It also has a reduction potential of positive 1.51 volts. Look at those two half reactions. You see how there's 2 electrons in the first one, 5 electrons in the second one, and they're both written on the left-hand side. These are both written as reductions. One of these is going to have to flip. We're also going to have to multiply through by 2 and 5, aren't we, to get 10 electrons? Let's hold on to that. Okay, what does it mean to completely describe something? Well, we got a few bullet points here. Number 1, 2, and 3. 1, you got to give the proper overall cell reaction, and it's got to be greater than 0, right? The whole process of running a spontaneous chemical reaction is to produce electricity, so E cell's got to be greater than 0. So we have to calculate that value. Number 3, we have to designate our anode and cathode. 4, we have to show the direction of electron flow and report the ions in each compartment. That basically just looks like we have to sketch the galvanic cell, right? And we will. All right, let's take a look at these two cell potentials to see which one of these guys do I have to flip. If I flip the MnO4 minus equation, I'm going to have a negative 1.51 volts. No good. We're going to end up with an overall cell voltage that's negative. We don't want that. So let's just flip the smaller one, the negative 0.44. In fact, flipping that makes it even more positive. So it says there with a little dash, probably written in the correct direction. They're referring to the plus 1.51 volts. Probably that one's written in the proper direction. We're going to flip the top one. We're going to flip the iron equation. And I'm doing that right now. See, I flipped it. Fe solid yields Fe2 plus 2 electrons. I like to line up my half reaction arrows, as you can see. I'm rewriting MnO4 minus plus 5 electrons plus 8H plus yields Mn2 plus 4H2O. Multiplying the top one by 5 to give me 10 electrons on the right. Multiplying the bottom one by 2 to give me 10 electrons on the left. You just aim to get those electrons to go away. You never have electrons in your final reaction. So the oxidation now, oxidation half reaction is positive 0.44 volts, and the reduction half reaction potential stays the same, 1.51 volts. Notice how I did not multiply through my E-ox or my E reduction by 5 or by 2. We don't do that. So what do we have? Multiplying through, 5 Fe solid yields 5 Fe2 plus 10 electrons. 2 MnO4 minus plus 10 electrons plus 16H plus yields 2 Mn2 plus 8H2O. Let's add things up. Let's get rid of my 10 electrons. That's all that got eliminated there. So I end up with 2 MnO4 minus plus 16H plus 5 Fe solid yields 5 Fe2 plus 2 Mn2 plus 8H2O. Okay? This is my balanced overall cell reaction. What is the standard cell voltage for this balanced reaction? 1.95 volts. All right, so that is how much is read on the voltmeter as electrons go from anode to cathode. We are going to do the galvanic cell, but let's go ahead and put it into line notation as well. Fe solid, that's the anodes on the far left. Fe solid, that's my electrode. In solution on the left is Fe2 plus. Compartment change, double line. MnO4 minus and Mn2 plus is in the cathode solution, and I have to use a platinum solid as my inert electrode on the right. So line notation, very good at telling us or how to translate just linearly what's going to go into the galvanic cell. And here is my galvanic cell sketch right now. I always make my anode on the left. That way I know that my electrons will go away from anode towards the cathode. My cathode is on the right. So anode where oxidation occurs. Cathode is where reduction occurs. So the anode is my oxidation. And over there, that electrode is Fe solid. And you can see I'm sketching how my electrons are going to flow with a measured voltage of 1.95 volts. There's my Fe solid in solution, Fe2 plus, that's my anode. In my cathode, the ions are MnO4 minus, Mn2 plus, H plus, and I have to use that inert conductor, right? That inert electrode, platinum. Okay, so that's a very pretty looking sketch, but it doesn't tell me anything really more than the line notation does. I guess it has 1.95 volts printed on it, where line notation doesn't tell you the actual voltage. But please remember, electrons for galvanic cells, okay? For electrochemical cells that are galvanic cells, electrons flow from anode to cathode. All right, example number 3, not going to be any different really than 1 and 2, but it's going to really help us to solidify our base or our groundwork awareness of galvanic cells before we can move forward in section 17. Example 3, given the following half reactions, describe completely the galvanic cell. These are both written as reductions. It's very obvious when you have the E and the E underneath each other, electron and electron. So who are we going to flip? Well, we're going to want to flip the 0.77, right? We've got to keep this thing overall positive. So it looks like the silver plus is going to get reduced, but the Fe2 plus is going to be oxidized. So we'll flip that at the top of our page of notes here. Because I am not flipping the silver plus half reaction, I'm just rewriting it right now. And my half reaction voltage, my E cell for that one, my E reduction is 0.80 volts. This is where reduction occurs, so it's going to be in my cathode. It'll be in my right-hand side compartment. And I flipped this one from the way it was given to me originally. I flipped the iron one. So it's now Fe2 plus yields Fe3 plus electron. And my oxidation potential is negative 0.77 volts because I flipped it. Summarize everything, I get to eliminate the electrons. Ag plus Fe2 plus yields Fe3 plus Ag solid. Thinking ahead here, you see how we only have Fe2 plus and Fe3 plus, no Fe solid? We're going to need a platinum electrode for that. So my overall cell voltage is a meager 0.03 volts. This reaction is not generating much electricity for us. Line notation, the oxidation is occurring with platinum at our electrode site. So platinum is the actual conducting metal, and Fe2 plus and Fe3 plus are in solution. Compartment divider, and then the cathode we have Ag plus in solution with Ag silver solid being our pricey electrode. All right, so now let's sketch it. All right, so the anode is on the left. That little, these little rectangles, they're supposed to be little metals, right? Those rectangles I draw. That is on the left. That's going to be platinum. The electrode I'm drawing on the right is going to be solid silver. Electrons flow from anode to cathode as we are starting to learn. Anode is where oxidation occurs. Cathode on the right is where reduction occurs. So in my solution for the anode, we have Fe2 plus and Fe3 plus. And in the right compartment, silver plus is in solution, and my silver solid is my actual electrode, my conducting material. All right. So we got a new page of notes here. I have gone through all three examples that kind of hammer home how to completely describe a galvanic cell. And in the next video, video number 4 from section 17, which is kind of like chapter 17, right? Electrochemistry. We're going to talk about the relationship between free energy, delta G. Remember that section 16 stuff? We're going to talk about the relationship between free energy, delta G, and these cell potentials that we've been learning about, E cell. All right, so please stick around for that video. It's coming up next, and you won't want to miss it. All right, see you soon.